So we've already been practicing how to find the general solution, and remember the general solution just means that I'm going to have this plus c at the end. And so here's just a picture of what a family of functions might look like based on what that c value is, and of course c is just moving that guy up or down is all it's doing. So what we're going to do in this short little lesson is to find a particular solution. In a particular solution, they're going to give us something called an initial condition, which is essentially a point that our graph will go through. And once we know a point that it's going to go through, same way if I said, here's an equation, y equals 2x plus c, and until I told you what c was, you wouldn't know where that graph was going to cross the y-axis. And therefore you could then graph it, and you couldn't really graph it until you knew what c was. It's the same idea. So what we're going to do is we're going to find the general solution the same way we've been practicing, and then we're going to use something called an initial condition to plug in an x value and a y value to solve for c. So let's take a look at this example. The original function was 3x squared minus 1. We found the antiderivative, or found the integral, which was x cubed minus x plus c. And then they told us that that function is going to go through the point 2, 4. So if we look at this graph over here, we're saying pick the one that goes through 2, 4. Well, what does that make c? So I'm going to take 2 for x, so 2 cubed, so I'm just taking x cubed, which is now 2, minus x plus c, and I'm setting it equal to y, which is 4, because that's part of my initial condition. And then from there, it's just algebra. So 2 cubed is 8 minus 2, that gives me 6. Subtract 6 from each side, that gives me negative 2 is c. So my particular solution, notice it no longer includes plus c. Now I've found that c is negative 2, and so I have my actual particular solution to this equation. So let's look at another example. They have given me the derivative of f of x, of big F of x, which is 1 over x squared. I want to find first the general solution. So again, I'm just going to use that power rule. I'm going to start by thinking of this guy as x to the negative 2, and then I'm going to integrate using the power rule. Remember, that means I'm going to take x to the 1 greater power than that, which is x to the negative 1, and I'm going to divide by negative 1. And of course add my plus c, and then rewrite it in a way that makes sense. From here, now I'm going to use f of 1 equals 0. So 0 is my y, so I'm going to say 0 equals negative 1 over x, which is 1, plus c, and I'm going to solve that. So again, I've plugged in 1 for f. I've had the plus c and then equals 0 because that's y. Solve for c to get that c is 1, because of course I would subtract c, so negative c equals negative 1, c equals 1. So my real solution then is f of x equals negative 1 over x, which is what I found over here, and instead of plus c, I'm going to use plus 1 because that's what I solved for c. And then I'm just keeping that same domain restriction that was given to me in the initial question. So here's an application, and this should look familiar to us. Previously when we did this, I didn't make you do any math to end up back at the position function. Essentially, I gave you the position function. I said s of t equals 1/2 g t squared plus v sub 0 of t plus s sub 0. This was the position function. So if I just said find the position function, which is one of the two questions here, I could skip all of this stuff that we're about to do and just go ahead and say s of t equals 1/2 times 32 feet per second, because that's our gravitational constant. The initial velocity is 64. The initial position is 80. And then, of course, I would reduce this to negative 16t squared plus 64t plus 80. So when I get done doing this question on the next page, or maybe the next after that, This is where I should have ended up, and I'm going to go about this the really, really long way, but I want you to understand where this came from to begin with. So let's take a look at information that I know. I know S of 0, which means position at time 0, is 80. I know S prime, remember S prime of t is velocity, so the velocity at time 0 is 64. And then I know S double prime, which is the acceleration, is negative 32, because that's what we use for acceleration due to gravity. So those are all my initial conditions that I'm going to use on the next page. So keep those in mind because I didn't rewrite them. So now what I'm going to do is I'm going to start from the end and work my way backwards, and notice when I get to the end I'm going to end up with that same function that I came up with on the last page, not doing any work, but this is where the position function came from. So S double prime of t is 32. I know that because it's acceleration due to gravity. So I'm going to integrate that, because if I integrate S double prime of t, then of course I'm going to end up at S of t. And that's what I want. So I'm going to, S prime of t, single prime. So I'm going to find S prime of t, which is the integral of S double prime of t. And so I'm integrating negative 32. And notice I'm using dt because we're dealing with t's, not x's. So if I integrate negative 32, it's negative 32t plus c. So far, so good. Now I have to use that initial condition that S prime of 0 is equal to 64, which was the initial velocity. So now I'm essentially taking this guy and finding the particular solution, which is what I've done here. And I find that when I solve negative 32 times 0 plus c equals 64, that c must be 64, and therefore S prime of t is negative 32t plus 64. And essentially I'm going to do all of that again. So now that I have integrated S double prime of t, I'm going to integrate S prime of t to end up with just S of t. And remember, S of 0, my initial condition S of 0 was 80, so that's the other thing I'm going to use. So notice here, to find S of t, I'm integrating S prime of t. This was S prime of t, which I found above. If I integrate that, I get negative 16t squared plus 64 plus c2, which is just another constant that I don't know the answer for. And that is, we're going to set all of that, I'm going to plug in 0 and set it equal to 80. And when I do that, I get 80. And therefore, my position function looks exactly like it did on my last page. The other part of that question says, when does the ball hit the ground? So that's the one I'm going to answer now. When does the ball hit the ground has nothing to do with integration or differentiation. It has everything to do with algebra. So what I'm going to do is I'm going to take this position function, and of course I know the ball hits the ground when the height is 0, so I'm replacing S of t with 0. And then I'm just solving. So you can factor, you can use the quadratic formula, etc. I chose to take out a GCF first and then factor what was left over. That gives me t equals 5 and t plus 1 equals 0, so t equals negative 1. And again, the negative value wouldn't make sense in the context of the question because time can't be negative, so the ball will hit the ground 5 seconds after it's thrown. So again, if we think of that in terms of a picture, it makes sense mathematically that at negative 1 and at 5 that my graph would hit the x-axis. So mathematically that makes perfect sense, but in real life we would really just close it off here because that's the positives. And so that's why it would make sense to only use the 5, because that's when the ball from this cliff at 80 feet would end up going up from there and then back down and hitting the ground at 5 seconds.